There is a planet called K218b. It is 124 light-years away in the constellation Leo. It is 8.5 times the mass of Earth. It orbits a red star once every 33 days. It may be covered in a global ocean beneath a sky of hydrogen. And in 2025, humanity's most powerful telescope detected what may be the chemical signature of life in its atmosphere. 2 independent instruments, 2 separate wavelength ranges, the same signal. The team spent months trying to get rid of it. They could not. Tonight, we go deep into the most compelling and contested scientific discovery of our time. The signal, the skeptics, the alien world, and what the answer, either way, means for everything. K218b, The Smell of Life. Chapter 1, The Smell of Life. But before we begin, if you enjoy these nighttime documentaries, remember to like and subscribe. It helps us bring you more videos like this. Now, let us begin. Somewhere in a Cambridge laboratory, a scientist stared at a readout and felt the floor shift beneath him. And in the weeks that followed, humanity quietly arrived at the edge of the most important question it has ever asked. Tonight, we are going to stand at that edge together and look down into it. It was April of 2025. Not a dramatic night, not a moment anyone had circled on a calendar. Just a Tuesday, somewhere, when the data finished processing and appeared on a screen in the Institute of Astronomy at the University of Cambridge. Niku Madhusudan had been waiting for these numbers for months. His team had already made one extraordinary detection back in 2023, using the James Webb Space Telescope's near-infrared instruments, a signal in the atmosphere of a planet 124 light-years away that should not have been there. A signal that pointed toward a molecule found on Earth in only one context: life. But one detection is not enough. Science demands more. So the team waited for a second observation window, this time using MIRI, the telescope's mid-infrared instrument. A completely different eye, looking through a completely different chemical window, at wavelengths that had zero overlap with the first detection. If the signal was real, it would appear again. If it was an error, a calibration ghost, a trick of the data, it would vanish. It did not vanish. Madhusudan described the moment later in an interview. He said it was a shock to the system, that it takes a while to recover from that, from the enormity of it. Those words, spoken carefully by a scientist trained to understate, trained to qualify, trained to doubt, carry more weight than any headline ever could. Because Niku Madhusudan is not a man given to drama. He is a man given to data. And the data had done something to him that data rarely does. It had left him stunned. The molecule his team detected is called dimethyl sulfide. You have smelled it. You may not have known what it was, but you have smelled it. Walk along any ocean beach. That particular smell of the sea, not the salt, not the seaweed exactly, but that sharp, slightly sulfurous, living smell that fills your lungs when the tide is out and the algae is baking in the sun. That is dimethyl sulfide. It is produced by marine phytoplankton, by billions upon billions of microscopic organisms living in the surface layers of Earth's oceans, exhaling this chemical as a byproduct of their metabolic lives. Every algae bloom, every kelp forest, every phytoplankton bloom that turns a stretch of ocean green in summer, all of it releasing this same molecule into the air. On Earth, nothing else makes it. Not volcanoes, not lightning, not atmospheric chemistry acting on its own. Dimethyl sulfide, in Earth's atmosphere, means life. It is as close to a biological signature as our planet produces. Now, that smell is radiating from a world 124 light-years away. Not at trace concentrations. Not at the levels you would find at a beach on a warm afternoon. At concentrations roughly 10,000 times higher than anything found in Earth's oceans. A planet that reeks of life. A planet so saturated with this molecule that if you could somehow place your nose against its atmosphere, the smell would be overwhelming. Incomprehensible. The combined output of every ocean on Earth, multiplied, and rising from a world we have never visited, orbiting a star we can barely see. Before you let that image carry you away, and it is an image worth sitting with, there is something important to understand about where we are in this story. This is not a confirmed discovery. The signal is real. The data exists. 2 independent instruments on the most powerful space telescope ever built have both detected it. But science has a threshold for claiming a discovery, and that threshold has not yet been crossed. We are close. Closer than we have ever been to finding life beyond Earth. But close is not there. And tonight, we are going to hold both of those things at the same time. The wonder and the rigor. The signal and the doubt. Because one without the other is not science. It is wishful thinking. You may have noticed that we have been here before. In 1996, scientists announced that a Martian meteorite found in Antarctica contained what appeared to be fossilized bacteria. President Clinton made a statement. The world held its breath. Years of analysis later, the structures turned out to be mineral formations, not fossils. The chemical markers that looked biological turned out to be contamination from Earth. The discovery collapsed under scrutiny, not because the scientists were dishonest, but because the desire to find life had moved faster than the evidence could support. Then, in 2020, a team announced the detection of phosphine on Venus. On Earth, phosphine is produced by bacteria and by industrial processes. Nothing natural in a planetary atmosphere should make it. The announcement sent the scientific community into a frenzy. Within months, reanalysis showed the spectral signature had been misidentified. It was almost certainly sulfur dioxide. The phosphine was not there. The story collapsed. Again. So why is K2-18b different? Because 2 completely separate instruments, looking through 2 completely separate wavelength windows, with 0 overlapping data, both returned the same signal. Because the detection matches a theoretical prediction made 4 years before the observation, a prediction published in a scientific paper in 2021 that said, if life exists on this type of planet, dimethyl sulfide will accumulate to exactly these concentrations. Because the team spent months after the first detection actively trying to find ways the signal could be wrong, they tested every calibration error. They modeled every alternative molecule. They looked for every possible explanation that did not involve life. The signal persisted. This does not mean life has been found. Madhusudhan himself has been precise about this. He says potential biosignature. He says possible indicators. He does not say life detected. But he also said something else in that same interview, something that is harder to qualify away. He said this is the first time in the history of our species that potential life indicators have been found on a habitable zone planet. Let that settle for a moment. The first time in the history of our species. Not the history of modern astronomy. Not the history of the space age. The history of our species. Every human being who ever looked up at the stars and asked whether something was looking back. Every philosopher and theologian and child lying in the grass on a summer night wondering. Every scientist who spent a career building the tools to ask the question properly. All of that accumulated wondering, all of that accumulated longing, is pointing at this moment. A planet called K2-18b, 124 light-years away, smelling of the sea. To understand what the signal means, and what it might not mean, we need to understand how humanity learned to smell another world from across the galaxy. We need to understand the instrument that made this possible, the telescope floating 1,000,000 miles from Earth, and the almost impossibly delicate technique it uses to read the chemistry of alien skies. We need to understand the planet itself, a world unlike anything in our solar system, massive and strange, and possibly covered in a global ocean beneath a sky of hydrogen. And we need to understand the scientists on both sides of this debate, the ones who believe the signal is biological, and the ones who believe there is a simpler, colder explanation. Because there is another possibility, and it involves a world not of water, but of fire. 2K2-18bs exist in the models. In one, an endless ocean stretches from horizon to horizon, beneath a sky the color of rust, alive with organisms we cannot yet imagine. In the other, a sea of molten rock glows in permanent twilight, and the smell of life is just chemistry, just heat and sulfur doing what heat and sulfur do in the dark. We do not yet know which one is real, but we are going to find out. K2-18b, The Smell of Life. Chapter 2, Reading the Light. There is a magic trick at the heart of modern astronomy. Not a metaphorical magic trick, not the kind of thing scientists say to make their work sound more exciting than it is. A genuine, almost incomprehensible feat of human ingenuity that allows us to sit here on this small planet and know what the air is made of, on a world orbiting a star so far away that the light reaching us left before the pyramids were built, before Rome, before the first human being picked up a stone and called it a tool. The light we collect from K2-18b tonight left that star 124 years ago, and buried inside that ancient light is a chemical diary of everything that world's atmosphere has been doing ever since. The technique is called transmission spectroscopy, and to understand it, you need to picture a very specific moment. K2-18b orbits its star, K-18, once every 33 days. During each orbit, there is a brief window, a matter of hours, when the planet passes directly between its star and us. From our perspective, the planet crosses the face of the star. This is called a transit. During a transit, something extraordinary happens to the starlight. Most of it is simply blocked by the planet's solid body. But at the very edges, at the thin ring where the planet's atmosphere meets the vacuum of space, some of the starlight passes through. It enters the atmosphere at one edge, travels through roughly 1,000 kilometers of alien air, and exits at the other side. And while it travels through that atmosphere, the molecules it encounters leave their mark on it. Every molecule in the universe absorbs light at specific wavelengths. Water absorbs at certain frequencies. Carbon dioxide absorbs at others. Methane has its own unique pattern. Dimethyl sulfide has its own pattern. Each one is like a barcode, a set of dark lines printed into the spectrum of the light that passes through them. When astronomers collect the starlight that has passed through K2-18b's atmosphere and spread it into its component wavelengths, they can read those barcodes. They can see which frequencies were absorbed, which molecules did the absorbing, and in what quantities. They can, in effect, smell the atmosphere of a planet they will never visit from a distance so vast it is essentially meaningless to the human mind. This would be impossible without the James Webb Space Telescope. Not difficult. Impossible. The signals we are talking about are extraordinarily faint. When K2-18b transits its star, the total dimming of the starlight is about 1%. The additional dimming caused by molecules in the atmosphere is a fraction of that. A fraction of a fraction. Detecting it requires a mirror large enough to collect vast quantities of photons. Instruments sensitive enough to distinguish between wavelengths separated by fractions of a micron, and a position in space stable enough that vibrations from engines or temperature changes do not swamp the signal you are trying to find. The James Webb Space Telescope has all of these things. Its primary mirror is 6.5 meters across, made of 18 gold-coated beryllium hexagons that unfolded in space like a flower. It orbits at the second Lagrange point, a gravitational equilibrium 1 million miles from Earth, where it stays in permanent shade behind a sunshield the size of a tennis court, keeping its instruments cooled to within a few degrees of absolute zero. It is, by any measure, the most complex scientific instrument humanity has ever built, and it was pointed at K2-18b not once, but twice, using two completely different sets of instruments to look for the same signal. The first observation, completed in 2023, used NIRSpec and NIRIS, the near-infrared spectrographs, which operate across wavelengths between roughly 0.8 and 5 microns. These instruments detected carbon dioxide, methane, and the initial hint of dimethyl sulfide. The second observation, completed in 2025, used MIRI, the mid-infrared instrument, which operates across a completely separate wavelength range, from 6 to 12 microns. Zero overlap. A completely different chemical window, looking for completely different absorption features. And the dimethyl sulfide signal appeared again. Think about what that means for a moment. Imagine you are trying to confirm whether a specific perfume is present in a room. You bring in one expert who samples the air and says they can detect it. Then you seal that expert outside, bring in a second expert with a completely different testing method, and they return the same answer. Neither expert could have influenced the other. The methods share no common assumptions. The results agree. That is the weight of what two independent instruments on the James Webb Space Telescope have now returned. But here is where the story becomes complicated in the way that all good science eventually does. The signal is strong. It is consistent. It has survived two independent observations and months of attempts by the detecting team to disprove it. And its current statistical confidence level is 3 sigma, which sounds impressive until you understand what it means in the context of scientific claims of this magnitude. 3 sigma means the probability that this signal is a random fluctuation, a noise artifact, a statistical accident, is roughly 3 in 1,000. In most fields of science, 3 sigma would be considered excellent evidence. You could publish on 3 sigma in chemistry, in medicine, in ecology, and no one would question your rigor. But in physics, and in the subset of astronomy that deals with discoveries of fundamental importance, the threshold is 5 sigma. 5 sigma means the probability of the signal being a statistical accident falls below 1 in 3.5 million. That is the threshold used to confirm the Higgs boson, the threshold used to confirm gravitational waves, and it is the threshold that any claim about biological signatures on another planet will need to meet before the scientific community accepts it as a discovery. The current K2-18b signal sits at 3 sigma. The gap between 3 sigma and 5 sigma is not a small bureaucratic formality. It is the difference between a compelling hint and an established fact. And crossing that gap requires more data. Specifically, 2 to 3 more transit observation windows, each one adding statistical weight to the signal, each one either reinforcing or eroding the detection. Given that K2-18b transits its star every 33 days, and given the extraordinary demand on the James Webb Space Telescope's observing schedule, those additional windows could come within 12 to 18 months of the 2025 announcement. Perhaps sooner. Perhaps the data already exists in a file somewhere, waiting to be processed. An Oxford astrophysicist named Jake Taylor applied a different statistical approach to the MIRI data, one that made no assumptions about which molecules to search for, and found what he described as results consistent with a flat line. No significant molecular features. A team at the University of Chicago combined the near-infrared and mid-infrared datasets and also found no statistical significance for dimethyl sulfide. Madhusudhan's team responded that these analyses used oversimplified atmospheric models. The critics disagreed. The debate has not been resolved. It is ongoing, active, and genuinely unresolved as of early 2026. This is not a story about scientists who found life. Not yet. This is a story about scientists who may be on the edge of finding it, who are arguing about what their instruments are telling them, who are building better methods and better models in real time, who are doing exactly what science is supposed to do when confronted with a signal that might change everything. They are demanding more, and so should we. But to understand what is truly at stake in this debate, we first need to understand the world itself, because K2-18b is not simply a distant planet where life might exist. It is one of the strangest worlds ever discovered, a class of planet that has no equivalent anywhere in our solar system, a world so alien in its physics and its possibilities that simply describing what it might look like requires us to abandon almost every assumption we carry about what a planet is supposed to be. And that description begins with a number, 8.6. 8.6 times the mass of Earth. What that number implies about the world it describes is something that took astronomers years to fully reckon with. K2-18b, The Smell of Life. Chapter 3. The planet that shouldn't exist. 8.6 times the mass of Earth. 2.6 times its radius. Those numbers sound simple. They sound like the kind of dry statistics that get listed in a catalogue and forgotten. But sit with them for a moment, because what they describe is a world so far outside our experience that our solar system offers no reference point at all. We have rocky planets: Mercury, Venus, Earth, Mars, small, dense, solid underfoot. We have gas giants: Jupiter, Saturn, Uranus, Neptune. Enormous, gaseous, with no surface to stand on. K2-18b is neither. It sits in a category that simply does not exist in our cosmic neighborhood. A sub-Neptune, a world too massive to be rocky, too small to be a true gas giant, with a density that falls somewhere between the two and a structure that planetary scientists are still arguing about. And it may be the most common type of planet in the entire galaxy. When the Kepler Space Telescope surveyed the sky between 2009 and 2018, cataloguing thousands of exoplanets for the first time, one category dominated the results in a way that surprised everyone. Not Earth-sized rocky worlds, not Jupiter-sized gas giants. Sub-Neptunes, planets between 1.5 and 4 times the radius of Earth, too large to be purely rocky. Apparently common everywhere the telescope looked. We had spent decades assuming our solar system was a reasonable template for what planets look like. Kepler told us we were wrong. The most abundant class of planet in the galaxy is one we have never been able to study up close, because we do not have one nearby. K2-18b is our best current window into what these worlds are actually like inside. The theoretical picture of K2-18b's interior goes something like this. At the center, a rocky core, perhaps similar in composition to Earth but under pressures that compress rock into exotic states we cannot replicate in any laboratory. Surrounding that, a layer of high-pressure ice, not the ice you find in a freezer, but water molecules locked into crystalline structures by pressures millions of times greater than anything at Earth's surface. Above that, possibly, a layer of liquid water, a global ocean with no land anywhere, no continents, no islands, no beaches, just water, extending from horizon to horizon across an entire planet. And above that ocean, a thick atmosphere of hydrogen and helium, stretching hundreds of kilometers into space, so massive that its weight creates surface pressures perhaps 100 times greater than what you feel standing at sea level on Earth. That is the Haitian model, hydrogen ocean world, a planet type proposed by Niku Madhusudan himself in a 2021 paper that has since become one of the most cited and most contested documents in modern planetary science. Haitian worlds, his paper argued, could be habitable across a far wider range of conditions than rocky planets like Earth. They could support liquid water at greater distances from their stars, or closer. They could maintain stable oceans for billions of years under hydrogen skies. And crucially, if life existed in those oceans, the molecules that life produced would accumulate in the hydrogen atmosphere to concentrations far higher than on Earth, because hydrogen atmospheres destroy certain biological molecules much more slowly than oxygen atmospheres do. Dimethyl sulfide in a hydrogen atmosphere has a lifespan roughly 10 to 100 times longer than in Earth's air, which means it builds up, which means a relatively modest biological source could produce the concentrations that JWST is now detecting. The theory predicted the observation before the observation existed. That kind of predictive success is rare in science, and it is part of why the Cambridge team takes the signal so seriously. But there is another model, and it paints a very different picture of the same world. K2-18b is 8.6 times the mass of Earth. At that mass, with that density, some planetary models suggest there is no ocean at all. Instead, what lies beneath the hydrogen atmosphere may be a magma ocean, a planet-wide sea of molten rock, glowing at temperatures of thousands of degrees, churning with convection currents that bring material up from the deep interior and drag it back down again. This is not a fringe idea. It is supported by serious modeling work from serious scientists, including a team at Cambridge, the same institution as Madhusudan, led by a planetary scientist named Oliver Shortall. Shortall's models show that a magma ocean world of this mass could dissolve nitrogen into the molten rock, which would explain why K2-18b's atmosphere appears to be missing the ammonia you would expect from a world of its composition. It can produce atmospheres rich in methane and carbon dioxide, atmospheres that look, from the outside, almost identical to a Haitian world. Same chemical fingerprint, completely opposite surface. One world is covered in water and potentially alive. The other is covered in lava and among the most hostile environments imaginable. And from 124 light-years away, using the most powerful telescope ever built, we cannot yet tell which one is real. That is the central tension of everything that follows in this documentary. Hold it in mind, because every piece of evidence, every argument, every observation comes back to this fork in the road. Now let us talk about K2-18b's year, because the planet's orbit adds another layer of strangeness to everything else. 1 year on K2-18b lasts 33 days. The planet completes its entire orbit around its star in roughly the time it takes Earth to move from 1 month to the next. This is not because K2-18b is moving unusually fast. It is because the planet orbits so close to its star, only about 13 million miles, compared to Earth's 93 million miles from our own Sun. And yet, despite that proximity, K2-18b sits comfortably within its star's habitable zone, the region where liquid water could theoretically exist on a surface. The reason is that K2-18, the star, is a red dwarf, a dim, cool, ancient star that burns at a fraction of the intensity of our Sun. The energy K2-18b receives at 13 million miles from that faint star is comparable to the energy Earth receives at 93 million miles from ours. The math works out. The habitable zone is just much, much closer. But that proximity comes with a consequence that shapes everything about K2 K2-18b's character. At 13 million miles, orbiting a star for billions of years, a planet almost certainly becomes tidally locked. Tidal locking is what happens to the Moon in its relationship with Earth. The same gravitational forces that create tides also, over long timescales, slow a body's rotation until one face permanently points toward the object it orbits. The Moon always shows us the same face. K2-18b almost certainly always shows the same face to its star. Picture what that means for a world. One hemisphere locked in permanent day, the red star hanging motionless in the sky, never rising, never setting, pouring radiation down on the same surface forever. Temperatures on the day side, potentially high enough to boil surface water, to break apart complex molecules, to strip the upper atmosphere layer by layer over geological time. The other hemisphere in permanent night, frozen and dark, temperatures plunging to perhaps 60 degrees below zero or colder, a landscape of perpetual shadow where the star is just a memory at the horizon's edge. And between them, a narrow ring, the terminator, the boundary where day becomes night, where the star sits permanently on the horizon, casting long shadows across a world that never turns away from it and never turns toward it. This strip of perpetual twilight, where temperatures are most moderate, where neither the blasting heat of the day side nor the deep freeze of the night side fully dominates, may be the most important real estate on the planet. If life exists on K2-18b, it likely concentrates here. In the thin band where conditions are survivable, where the chemistry of light and dark meets, where the atmosphere churns and the ocean, if there is an ocean, circulates heat from one hemisphere to the other. The atmosphere itself would be in constant violent motion. The day side heats the hydrogen air, which expands and rises and flows toward the night side, where it cools, contracts, sinks, and flows back. A planetary circulation system driven not by the seasonal rhythms that govern Earth's weather, but by the permanent, unrelenting temperature difference between a hemisphere that faces a star and a hemisphere that faces the void. Wind speeds along the terminator could reach hundreds of miles per hour. A constant roar of hydrogen rushing around the planet, carrying heat from the baking day side and delivering it to the frozen night. This is K2-18b, a world of extremes, a world that should not, by the standards of our solar system, exist at all. A world that may be covered in a global ocean alive with microbial life, or covered in a global ocean of molten rock. A world where the sun never moves in the sky and the wind never stops. And a world, somewhere out there in the dark between the stars, that smells like the sea. To understand how this world came to be in its current state, and why the star it orbits may be simultaneously its greatest threat, and the reason we can study it at all, we need to talk about the nature of red dwarfs. Because K2-18, the star, is not simply a smaller, dimmer version of our Sun. It is a fundamentally different kind of object. And what it does to the planets in its care is something our Sun has never done to us. K2-18b, the smell of life. Chapter 4, the red dwarf problem. Most stars in the galaxy are trying to kill their planets. Not through some violent cataclysm, not through the kind of spectacular destruction that fills science fiction films, but slowly, relentlessly, over billions of years, through a constant assault of radiation and charged particles and electromagnetic fury that makes our own Sun look like a candle in a storm. K2-18 is one of these stars, a red dwarf. And understanding what that means for K2-18b, what it means for any planet unlucky enough to orbit one of these ancient, violent objects, is essential to understanding whether life there is possible at all. Red dwarfs are the most common stars in the Milky Way. Estimates suggest they make up roughly 70 to 75% of all stars in our galaxy. If you picked a random star from the 400 billion in the Milky Way, chances are better than 2 to 1 that you would pick a red dwarf. They are everywhere. They are ancient. Some of the red dwarfs burning today have been burning since the universe was less than 1 billion years old, and they will still be burning long after our sun has exhausted its fuel and collapsed. Red dwarfs are miserly with their hydrogen, fusing it so slowly that a red dwarf of modest mass could live for 10 trillion years. Our sun, by comparison, has a total lifespan of roughly 10 billion years. It is already middle-aged. A red dwarf at the same age would be barely out of infancy. But longevity comes at a cost. Or rather, youth comes at a cost. In their early lives, red dwarfs are extraordinarily violent. They erupt with stellar flares, bursts of X-rays and ultraviolet radiation, and charged particles that can be thousands of times more powerful than the largest flares our sun produces. These events can occur daily, sometimes multiple times a day. A planet orbiting close enough to receive habitable zone levels of warmth from one of these stars is also orbiting close enough to be bathed in radiation doses that would sterilize the surface of Earth many times over. Every flare is a potential biosignature destroyer. Every surge of X-rays can split molecules in the upper atmosphere, accelerating chemical reactions that might mimic or mask biological signals. Every blast of charged particles can erode the upper layers of the atmosphere, slowly peeling away the very envelope that makes the planet habitable. K2-18 is approximately 2.4 billion years old. For a red dwarf, that is not young, but it is not ancient either. It is considered relatively calm for its type, which is to say it still flares regularly, still bombards its planets with radiation, but not at the extreme rate seen in younger, more active red dwarfs. K2-18b orbits at 13 million miles from this star. For comparison, Mercury, the closest planet to our own sun, orbits at 36 million miles. K2-18b is nearly 3 times closer to its star than Mercury is to ours. And yet, because K2-18 is so much dimmer than our sun, the amount of energy K2-18b receives is comparable to what Earth receives. The habitable zone math works, but the radiation environment is nothing like Earth's. Here is the paradox at the heart of red dwarf research. These stars are simultaneously the most dangerous hosts for life and the most useful for finding it. Dangerous because of the radiation, the tidal locking, the stellar winds that constantly pressure the atmosphere. Useful because their habitable zones are so close to the star that planets transit much more frequently and much more visibly than they would around larger, brighter stars. A planet in the habitable zone of a sun-like star might transit once a year, and each transit lasts only a few hours. A planet in the habitable zone of a red dwarf transits every few weeks, sometimes more often, and each transit is easier to detect because the planet is large relative to the small star. Red dwarf planets are, in the language of astronomers, observable. They are the low-hanging fruit of the exoplanet atmosphere game, which is why K2-18b, despite being so far from a comfortable world by any measure, is the planet we know most about. K2-18b has retained its massive hydrogen atmosphere for over 2 billion years, despite the constant bombardment from its star. That fact alone deserves attention. Mars lost its atmosphere to solar wind roughly 3 to 4 billion years ago, when the planet's magnetic field weakened and the charged particles from our sun began stripping away the air molecule by molecule. Venus survived atmospheric loss, but ended up with a runaway greenhouse effect that turned it into a hell of 460-degree heat and sulfuric acid clouds. Earth retained a hospitable atmosphere partly because of its strong magnetic field, generated by the churning iron core at its center, which deflects solar wind like a planetary shield. K2-18b, facing radiation many times more intense than Earth receives, has kept its atmosphere for billions of years. Why? The honest answer is that we do not fully know. several explanations have been proposed. The planet may have a strong internal magnetic field generated by its massive hot interior, a shield that deflects stellar wind and prevents atmospheric stripping. Its hydrogen atmosphere is so thick and so massive that even significant losses over billions of years represent only a small percentage of the total envelope. There may be continuous replenishment from volcanic outgassing or from chemical reactions in the interior that release hydrogen into the atmosphere as fast as it is lost. Whatever the mechanism, the fact that the atmosphere has survived is itself a kind of evidence. A planet that has maintained a stable atmosphere for 2 billion years in the face of constant stellar assault is a planet that has some form of protection. Whether that protection comes from a magnetic field or atmospheric mass, or some process we have not yet identified, it suggests a world that has been geologically and atmospherically active across a timescale long enough for life to have gotten started. On Earth, life appeared within roughly 500 million years of the planet's formation. K2-18b has had over 2 billion years. If the conditions were right, that is an enormous amount of time. But the conditions imposed by a red dwarf do more than just threaten the atmosphere. They shape the chemistry of everything inside it. When K2-18 flares, the ultraviolet radiation that reaches K2-18b drives photochemical reactions in the upper atmosphere. These reactions can destroy complex molecules, including dimethyl sulfide, which is broken apart by UV light in Earth's atmosphere within a matter of days. This is actually one of the reasons the DMS signal is considered potentially significant. In a hydrogen atmosphere, shielded from UV by the overlying gas, dimethyl sulfide survives much longer than it does on Earth. But if the flare rate of K2-18 is high enough, if UV pulses reach the lower atmosphere during major eruptions, DMS could be destroyed faster than it accumulates. This creates a constraint on the biology, if biology is the source. Whatever organisms might be producing DMS in K2-18b's ocean, they would need to be producing it continuously, in enormous quantities, against a background of periodic destruction from above. They would need to be resilient, radiation tolerant, capable of surviving conditions that would kill most organisms on Earth. But we already know that life can do this. Deinococcus radiodurans, a bacterium found on Earth, can survive radiation doses 10,000 times greater than what would kill a human being. It has been found in nuclear reactors, in the stratosphere, in the dry valleys of Antarctica. Life, when it gets a foothold, is extraordinarily difficult to kill. There is one more thing that K2-18's nature as a red dwarf tells us, and it is something that cuts both ways in the search for life. Red dwarfs emit most of their light in the near-infrared, not in the visible spectrum. A planet orbiting K2-18 would receive a very different quality of light than Earth receives from our Sun. The red and infrared light that dominates K2-18's output penetrates deeper into water than visible light does on Earth, which means that if there is an ocean on K2-18b, photosynthesis, or whatever process organisms might use to harvest energy from starlight, could potentially occur at greater depths than on Earth. The entire water column becomes potentially illuminated, not just the top few meters. This could dramatically expand the habitable volume of the ocean, allowing life to spread through layers of water that on Earth are in permanent darkness. Or it could mean nothing, because there is no ocean, because the surface is lava, because the beautiful, intricate biology we have been imagining in the last few minutes is a construction made of wishful thinking and inadequate data. The red dwarf is not trying to answer our questions. It is simply burning, as it has burned for 2 billion years, indifferent to the small blue telescope 1 million miles from a small blue planet that is pointing at its third world and asking whether anything lives there. The star does not know we are watching, but we are watching, and the light that reaches us carries secrets. We just have not finished reading them yet. K2-18b. The Smell of Life. Chapter 5. Inside the Hycean World. In 2021, a scientist sat down and imagined a type of planet that had never been formally described before. Not because the planet type was new, but because no one had looked at sub-Neptunes through the specific lens of habitability and asked, seriously and systematically, whether life could survive in these conditions. Niku Madhusudan and his collaborators published a paper that year in the Astrophysical Journal titled Habitability and Biosignatures of Hycean Worlds. It introduced a concept, a framework, and a prediction. The concept was the Hycean world itself. The framework described the conditions under which a sub-Neptune with a hydrogen atmosphere could maintain liquid water oceans, and the prediction was specific enough to be tested. If life exists in a Hycean ocean, dimethyl sulfide will accumulate in the hydrogen atmosphere to concentrations detectable by the James Webb Space Telescope. 4 years later, JWST detected dimethyl sulfide at K2-18b. The predictive power of that sequence deserves emphasis, because it is easy to lose in the noise of the debate that followed. The Cambridge team did not look at the data and then construct a theory to explain it. They constructed the theory first, derived a testable prediction from it, waited for the telescope to collect the data, and found that the data matched the prediction. This is the scientific method working exactly as it is supposed to work. It does not prove the theory is correct, but it is the strongest form of scientific evidence available. A prediction made before the observation, confirmed by the observation, is worth far more than a theory invented to explain data that already exists. So what exactly is a Hycean world? And why might it be habitable when it seems, on its face, so deeply hostile? The name comes from the combination of hydrogen and ocean. A Hycean world is a sub-Neptune with a thick hydrogen and helium atmosphere and a global liquid water ocean beneath it. No continents, no land at all, just water, extending to depths we cannot yet measure, under a sky of hydrogen so thick that its weight creates pressures at the ocean surface, perhaps 100 times greater than sea level pressure on Earth. The atmospheric mass alone contributes significantly to the greenhouse warming that keeps the ocean liquid. Hydrogen is not an efficient greenhouse gas molecule by molecule, but when you have an atmosphere massive enough that its sheer weight creates significant pressure, even a modestly efficient greenhouse effect adds up to substantial warming. On K2-18b, this effect keeps the ocean liquid despite the planet being further from its star than a naive calculation might suggest it could be. Here is something that surprises most people when they first encounter it. Hydrogen, the gas that composes the vast majority of K2-18b's atmosphere, is not toxic to all life. We tend to assume that life requires oxygen. That breathable air, the kind that supports complex biology, must contain significant amounts of the gas that powers animal metabolism. But that assumption comes entirely from our experience of life on Earth, and Earth's oxygen-rich atmosphere is itself a biological product. For the first 2 billion years of life on Earth, the atmosphere contained almost no free oxygen. Life thrived anyway. Anaerobic organisms, creatures that live without oxygen, still make up a vast portion of Earth's total biomass. They live in deep-sea sediments, in volcanic hot springs, in the oxygen-free layers of the ocean, in the guts of every animal that has ever walked the planet. They do not merely tolerate the absence of oxygen. Some of them are actively harmed by its presence. Oxygen, to them, is a poison. Experiments placing Earth bacteria in pure hydrogen atmospheres found that the bacteria survived. They did not immediately die. They continued metabolic activity. Some microorganisms, the methanogens, actively use hydrogen as a fuel source. They combine hydrogen gas with carbon dioxide and produce methane and water as waste products. K2-18b has an atmosphere rich in hydrogen. It has detectable carbon dioxide. It has abundant methane. If methanogens were present in a Haitian ocean on K2-18b, producing methane as metabolic waste, the atmospheric signature would look almost exactly like what JWST is observing. That alignment is not proof, but it is the kind of coincidence that keeps scientists up at night. The ocean itself, in the Haitian model, would be one of the strangest bodies of water ever conceived. Water at surface pressures 100 times greater than Earth's atmosphere does not behave like the water in your glass. Its boiling point rises dramatically. Under enough pressure, water can remain liquid at temperatures well above 100 degrees Celsius. At truly extreme pressures, it enters a supercritical state, where the distinction between liquid and gas disappears entirely, and you have a dense, flowing fluid with properties of both. Whether K2-18b's ocean surface would be liquid water, supercritical water, or something in between depends critically on temperature. And temperature, in turn, depends on cloud cover. Clouds are the wild card in every atmospheric model. Bright clouds reflect starlight back into space, cooling the planet. Dark skies, or clouds that form low and trap heat, warm it. On K2-18b, if clouds form at the right altitude and achieve the right optical depth, they could reflect enough starlight to keep surface temperatures within the range where liquid water exists. If they do not form, if the upper atmosphere is relatively clear, then more starlight reaches the surface, temperatures rise, and the ocean either boils away or becomes supercritical fluid, incompatible with life as we understand it. Current JWST data does not show strong evidence for the dense reflective cloud layers that the liquid ocean model requires. This is one of the most significant challenges the Haitian hypothesis currently faces. And yet, cloud modeling is among the most difficult problems in planetary science. We cannot fully model the clouds of Earth, a planet we can fly through and measure directly. Modeling the clouds of a world 124 light-years away from incomplete spectroscopic data is a problem so difficult that the uncertainty ranges are enormous. The absence of evidence for clouds in current data does not mean clouds are absent. It means we have not yet conclusively detected them. These are different statements. And the distinction matters enormously for what the planet's surface looks like. There is one more feature of the Haitian world that deserves attention, and it connects back to the signal itself. On Earth, dimethyl sulfide is produced primarily by marine phytoplankton, microscopic photosynthetic organisms that live in the sunlit surface layers of the ocean. They produce it as a byproduct of breaking down a compound called dimethyl sulfonneopropionate, which they use as an osmotic regulator, a chemical that helps them manage the salt concentration in their cells. The DMS is essentially accidental, a waste product of a process that evolved for a completely different purpose. In K2-18b's ocean, assuming for a moment that organisms exist, the biochemistry would almost certainly be different. There is no reason to expect that alien microbes in a high-pressure hydrogen sky ocean would use the same metabolic pathways as Earth phytoplankton. The DMS, if it is biological, might be produced by a completely different mechanism, perhaps as a direct metabolic product, perhaps as a chemical signal between organisms, a kind of molecular language, the way some bacteria on Earth use chemical signals to coordinate collective behavior. Perhaps as a byproduct of sulfur cycling in the ocean, organisms metabolizing sulfur compounds the way Earth bacteria metabolize iron or nitrogen. We do not know. We cannot know from this distance, with these instruments, at this stage of the investigation. What we know is that the molecule is there, or appears to be there, in concentrations that require either an enormous amount of biological activity or an as yet unidentified abiotic process. The Haitian model provides a plausible framework for the biology. It does not prove the biology is real. But it tells us that the biology, if real, would be physically possible on this world, that a hydrogen ocean world could support microbial life, that the conditions we are observing from 124 light-years away are at least in the right territory. The Haitian world is a beautiful idea, elegant in its construction, coherent in its predictions, extraordinary in its implications. But beautiful ideas in science must survive contact with their critics. And the critics of the Haitian hypothesis are not fringe voices. They are some of the most rigorous planetary scientists working today. And they have built a case, piece by careful piece, that K2-18b is not a water world at all. Their argument begins with a simple question about mirrors. K2-18b. The Smell of Life. Chapter 6. The Case Against Life. Science does not advance by confirming what we hope is true. It advances by failing to prove what we hope is false. The distinction sounds subtle, but it is everything. And nowhere is it more important than in the search for life beyond Earth, where the desire to find a positive result is so powerful, so culturally embedded, so emotionally loaded, that the scientific immune system has to work twice as hard to prevent wishful thinking from masquerading as evidence. The scientists who are skeptical of the K2-18b biosignature claim are not pessimists. They are not hostile to the idea of life in the universe. They are doing exactly what the situation demands. They are pushing back, hard, and their arguments deserve to be heard in full. The first, and perhaps most physically fundamental challenge to the Haitian interpretation is what researchers have started calling the albedo crisis. Albedo is a measure of how reflective a surface is. Fresh snow has an albedo close to 1, meaning it reflects nearly all the light that hits it. A dark ocean has an albedo close to 0, meaning it absorbs nearly all incoming light. Earth's average albedo, combining oceans, land, clouds, and ice, sits at roughly 0.3. It reflects about 30% of incoming sunlight back into space. 2 independent research teams published analyses in 2025 examining what albedo K2-18b would need in order to maintain liquid water at its surface. At the surface pressures implied by its massive atmosphere, roughly 10 bars or more, water would not boil until temperatures far exceeding 100 degrees Celsius. But the star still pours energy into the day side. For the planet to stay cool enough for liquid water, it needs to reflect the vast majority of that energy back into space. The calculation came back with a number that stopped both teams in their tracks. K2-18b would need an albedo of approximately 0.92, 92% reflectivity, essentially a perfect mirror, reflecting 19 out of every 20 photons that arrive from the star. No known planet achieves this. No known atmosphere produces it. And crucially, current JWST observations of K2-18b show no evidence of the extremely dense, high-altitude cloud layers that would be required to generate such extraordinary reflectivity. If this analysis is correct, the surface of K2-18b is not covered in liquid water. The surface is too hot, and if there is no liquid water ocean, the Haitian hypothesis collapses, along with the biological interpretation of the DMS signal. The second major challenge comes from a team based, remarkably, at the same institution as Madhusudhan. Oliver Shortall is a planetary scientist at the University of Cambridge. His group has spent years building models of what sub-Neptune interiors actually look like, taking into account the chemistry that happens when a hot, high-pressure rocky mantle interacts with a thick, overlying atmosphere. The results are uncomfortable for the Haitian hypothesis. In a magma ocean world, molten rock at the base of the atmosphere dissolves gases from above and releases others from below in a continuous exchange that shapes the atmospheric composition. Nitrogen, which should be abundant in the atmosphere of a world with K2-18b's mass and composition, gets dissolved into the magma. This explains the low ammonia signal that Madhusudan's team originally cited as evidence for the Hessian model. In the Hessian model, the absence of ammonia is explained by biological processes consuming it. In the magma ocean model, the absence of ammonia is explained by simple chemistry. The magma eats it. Shortall's models produce atmospheres that are rich in methane and carbon dioxide, poor in ammonia, and consistent with the overall spectral fingerprint that JWST has observed. The same atmospheric composition. A completely different surface. One world is a warm hydrogen ocean potentially alive with microbes. The other is a planet-wide sea of glowing molten rock, with a chemistry that mimics life without containing any. The magma ocean scenario even provides a potential pathway to explaining the DMS signal itself. At very high temperatures, methane reacts with hydrogen sulfide, a volcanic gas commonly released by molten rock, to produce sulfur-containing organic compounds. Laboratory experiments have confirmed that this reaction pathway exists and can produce dimethyl sulfide under the right conditions. The yields are low, perhaps 10 to 100 times lower than would be needed to explain the observed signal. But those yields were measured under Earth laboratory conditions, not the extreme pressures and temperatures of a planetary interior. The actual yields on K2-18b, if the surface is indeed magma, are unknown. This is the frustrating reality of the current situation. Both explanations are plausible. Neither is proven. And the data that would distinguish between them, higher resolution spectroscopy, direct measurement of cloud altitude and density, detection of additional molecules that would be present in one scenario and absent in the other, that data does not yet exist. The third challenge comes not from the planet's interior but from the statistics of the detection itself. When Oxford astrophysicist Jake Taylor applied what he described as an unbiased retrieval analysis to the MIRI data, he was using a method that makes no prior assumptions about which molecules to search for. You feed in the spectrum, you ask the algorithm to find the best fit model, and you see what it returns. Taylor's analysis returned a result consistent with a flat line. No statistically significant molecular features. The spectrum, by his method, was not clearly distinguishable from noise. A team at the University of Chicago then combined the near-infrared data from 2023 with the mid-infrared data from 2025 and performed a joint analysis. Their conclusion was similar. When both datasets were considered together, there was no statistically significant detection of dimethyl sulfide or dimethyl disulfide. Madhusudan's team pushed back on both analyses. They argued that Taylor's method used an oversimplified atmospheric model that could not reliably distinguish between molecules with overlapping spectral features at the resolution JWST provides. They argued that the Chicago team's joint analysis made assumptions about the relative weighting of the two datasets that were not physically justified. The critics argued that Madhusudan's team was fitting a model with too many free parameters, tuning it until it produced the result they were looking for. The team expanded their atmospheric chemical model to include 650 molecules and concluded that dimethyl sulfide remained the most plausible explanation. Critics noted that the analysis had changed significantly without any new data arriving. This is science in real time. Messy, contested, unresolved. Not the clean narrative of discovery that gets written in textbooks years later, but the actual process, full of disagreement and uncertainty, and the very human difficulty of knowing when a signal is real. There is one more piece of evidence that complicates the biological interpretation, and it comes from an unexpected place. The Rosetta spacecraft, which spent 2 years studying Comet 67 P. Churyumov-Gerasimenko before landing on its surface in 2016, collected detailed chemical measurements of the comet's volatile compounds. When researchers went back through the Rosetta data in recent years, they found something that had gone largely unremarked at the time: dimethyl sulfide in cometary ice. Comets are ancient objects, relics of the early solar system, composed of the same primitive materials that assembled planets 4.5 billion years ago. No biology, no life, just chemistry, ancient and cold and indifferent. And yet there was the molecule, the same molecule whose detection in K2-18b's atmosphere is being considered a potential biosignature. Dimethyl sulfide can form abiotically. It does form abiotically. We have direct evidence of it forming in space, in the absence of any life whatsoever. The question is not whether abiotic DMS exists. The question is whether the concentrations seen at K2-18b, 10,000 times higher than Earth's oceans, can be explained by abiotic processes alone. The honest answer, in early 2026, is that we do not know. We have not fully characterized all the abiotic chemical pathways available on a world like K2-18b. We have not determined the temperature and pressure conditions at the atmosphere-ocean or atmosphere-magma interface well enough to calculate abiotic DMS yields precisely. We are working at the edge of what we can measure, with instruments that were not designed for exactly this problem, interpreting data that is genuinely ambiguous. The case against life at K2-18b is not a fringe position. It is not the complaint of scientists who are closed-minded about extraterrestrial biology. It is a serious, evidence-based argument made by serious people that the extraordinary interpretation requires more extraordinary evidence than currently exists. Laura Kreidberg, a respected exoplanet scientist at the Max Planck Institute, said simply that she had seen this movie before. She was referring to past claims, including the Hubble water detection that turned out to be methane, the phosphine on Venus that turned out to be sulfur dioxide. Christopher Glein at the Southwest Research Institute put it more bluntly. He said that unless we see something waving at us, it is not going to be a smoking gun. They are right. It is not a smoking gun, but it is smoke. And the question of whether there is a fire behind it is the question that is going to define the next decade of human astronomy. K2-18b, The Smell of Life. Chapter 7. The History of False Positives. On August 7th, 1996, President Bill Clinton walked to a podium in the Rose Garden at the White House and made an announcement that stopped the world. He said that a team of NASA scientists had found compelling evidence that might point to the possibility of ancient, primitive life on Mars. He said that if confirmed, this would surely be one of the most stunning insights into our universe that science has ever uncovered. He was speaking about a meteorite, a piece of rock, roughly the size of a potato, that had been blasted off the surface of Mars by an asteroid impact billions of years ago, drifted through space for millions of years, fallen through Earth's atmosphere, and been found in the ice of the Allen Hills region of Antarctica in 1984. It was called ALH 84001, and what scientists thought they saw inside it would haunt the search for extraterrestrial life for decades. The evidence seemed remarkable at the time. Microscopic structures that resembled fossilized bacteria, far smaller than any known Earth bacterium, but structurally suggestive. Chemical compounds called polycyclic aromatic hydrocarbons, which are produced when organic molecules break down. Carbonate mineral globules that on Earth are sometimes associated with biological activity, and magnetic crystals of magnetite that looked similar to those produced by certain bacteria on Earth. Taken together, the NASA team argued these features were consistent with ancient Martian microbial life. Not proof, consistent with, but the nuance was lost in translation. The world wanted it to be true, and that wanting is where the trouble begins. Over the following years, careful analysis dismantled each piece of the evidence one by one. The microfossil structures turned out to be far smaller than any known living cell, and experiments showed that similar structures could form through purely inorganic chemical processes. The polycyclic aromatic hydrocarbons were found throughout the meteorite, including in regions that would have been exposed to Antarctic contamination from Earth organisms. The carbonate globules could be explained by high-temperature chemical reactions with no biological involvement. The magnetite crystals, the most compelling piece of evidence, remain genuinely debated even today, with some researchers still arguing they show biological signatures and others maintaining they are abiotic. But the overall case collapsed, not because the scientists were dishonest or incompetent, because the evidence, when examined rigorously, was insufficient, and because the desire to confirm a discovery had moved faster than the evidence could support. The Martian meteorite episode became the defining cautionary tale of astrobiology. It shaped the culture of the field. It created an institutional wariness about extraordinary claims, a reflexive demand for multiple independent lines of evidence, before anyone even considers using words like discovery or confirmed. That wariness is part of why the K2-18b announcement was greeted with such immediate skepticism, even from researchers who found the data genuinely interesting. The scar tissue from 1996 is still there. Then came 2020, and Venus. A team led by Jane Greaves at Cardiff University announced the detection of phosphine in the atmosphere of Venus. Phosphine is a molecule consisting of one phosphorus atom and 3 hydrogen atoms. On Earth, it is produced in 2 contexts: industrial chemical processes and anaerobic bacteria living in oxygen-free environments like swamps, marshes, and the intestinal tracts of animals. No known natural abiotic process in a planetary atmosphere should produce significant quantities of phosphine, which meant that if phosphine was genuinely present in Venus's atmosphere, something was making it, and the most plausible something was life. The announcement was enormous. Media coverage was immediate, breathless, and almost universally presented the finding as evidence of life on Venus. Researchers who had spent careers studying Venus were flooded with interview requests. The planetary science community convened urgent discussions. For several weeks, it seemed as though the question of life in the solar system might be about to be answered at the planet next door. Then the reanalysis began. Multiple research groups looked at the original spectral data used by the Cardiff team. They found problems. The signal that had been identified as phosphine was at a wavelength that overlaps with absorption features from sulfur dioxide, a gas that Venus has in abundance. The data reduction pipeline used by the Cardiff team had a calibration error that artificially amplified the signal. When corrected, the phosphine detection dropped from 20 parts per billion to approximately 1 part per billion, a level potentially explainable by ordinary photochemistry with no biology required. Further reanalysis by several independent groups found no convincing evidence for phosphine at all. The detection was almost certainly an artifact, a ghost in the data created by overlapping spectral features and imperfect calibration. Life on Venus had not been found. A lesson had been. The lesson was not that the Cardiff team were bad scientists. They were not. The lesson was about the structure of the problem. Biosignature detection at the limits of instrument sensitivity, using spectral features that overlap with other compounds, in atmospheric conditions that are poorly understood, is extraordinarily prone to false positives. Is less than #0, 3# is greater than. Not because researchers are careless, but because the signal-to-noise problem is genuinely hard. The number of alternative explanations is genuinely large, and the human tendency to find what you are looking for is genuinely powerful. K2-18b is following the same script with unsettling precision. Extraordinary spectral claim. Immediate media frenzy presenting the result as near confirmation of life. Swift pushback from the community. statistical reanalyses finding different conclusions from the same data, defending team arguing the critics used inadequate methods, critics arguing the detecting team overfit their models. The pattern is so similar that several scientists have explicitly drawn the comparison. One of them was Laura Kreidberg. She had seen this movie before. And yet, there is a reason K2-18b is not simply another phosphine story. Several reasons, actually. The phosphine detection was a single instrument, a single observation, a single spectral feature that had a direct, mundane explanation. K2-18b's DMS signal has been seen by two independent instruments looking through completely separate wavelength windows. The detection has survived multiple attempts by the detecting team to disprove it. It was predicted by theory before it was observed. And the statistical confidence, while below the 5 sigma threshold for discovery, has not collapsed the way the phosphine signal collapsed when reanalyzed. It has been contested. It has not been disproven. The history of false positives in astrobiology is not a history of failure. It is a history of refinement. The Martian meteorite episode drove investment in contamination detection protocols that transformed the field. It forced astrobiologists to develop much stricter criteria for what counts as a biosignature, pushing the community toward the concept of biosignature ensembles, multiple co-occurring molecules that together are difficult to explain without life, rather than single molecules that each have individual abiotic escape routes. The phosphine controversy produced better spectral analysis methods, better calibration protocols, and a broader awareness of how easily overlapping molecular features can mislead even careful researchers. It also produced a more complete catalogue of potential biosignature molecules and a deeper understanding of which ones are most and least prone to false positives. The K2-18b debate is already producing similar progress. Jake Taylor's unbiased retrieval method, developed partly in response to the DMS controversy, represents a genuine methodological advance. The magma ocean modeling work from Oliver Shortall's group has produced the most comprehensive treatment of magma atmosphere chemistry in sub-Neptunes ever published. Sarah Seeger at MIT published a preprint in 2025 identifying 15 candidate biosignature gases for exoplanet atmospheres, a catalogue that emerged directly from the need to go beyond single molecule detections. The search for life advances even when individual claims fall apart. Sometimes, especially then. Eddie Schwieterman, an astrobiologist at the University of California, Riverside, said plainly that it would not be surprising if the signal went away. He was not being dismissive. He was being honest. Most extraordinary claims in science, when subjected to sufficient scrutiny, turn out to have ordinary explanations. That is not a failure of the process. That is the process working. The purpose of science is not to confirm our hopes. The purpose is to find out what is actually true, wherever that leads. And what makes K2-18b different from every previous false alarm is not the strength of the current evidence. It is what comes next. Because we can get more data, the planet is still out there. The telescope is still operational. The observation queue is already being petitioned. We are not waiting for a mission to launch or a technology to be invented. We are waiting for the planet to cross its star again. And it will. Every 33 days. Patient, indifferent, carrying its secrets in its atmosphere, waiting for us to develop the rigor to read them correctly. K2-18b, The Smell of Life. Chapter 8. What life on K2-18b would actually be like? Let us assume, for the duration of this chapter, that the signal is real, not confirmed, not proven, but real. Let us follow that assumption wherever it leads and ask a question that no scientist has yet been able to answer with data, only with imagination and biology and the hard logic of chemistry. If something is alive in the ocean of K2-18b, what is its life actually like? What does it face every single day of its existence on that alien world? What does it need to survive? And how different would it be from anything that has ever lived on Earth? Start with time. K2-18b completes one orbit every 33 days. That is the length of its year. But unlike Earth, where the year brings seasons because our planet is tilted on its axis and our distance from the Sun varies only slightly, K2-18b's year brings something more dramatic. Its orbit is not perfectly circular. It is slightly elliptical, meaning the planet swings closer to its star and then farther away over the course of each 33-day cycle. The variation in received starlight between the close approach and the far point is roughly 43%. Every orbit, the energy input to the planet changes by nearly half. Temperatures at the ocean surface, if there is an ocean surface, likely swing by 20 degrees Celsius or more in a matter of weeks. Not gradually, the way Earth's seasons shift over months, but in the compressed rhythm of a world on a fast, tight orbit around a volatile star. For life, this is a significant challenge, but it is not an insurmountable one. Consider what bacteria on Earth do when conditions become hostile. Many form spores, dormant survival structures so tough they have been revived after millions of years embedded in rock, after exposure to the vacuum of space, after doses of radiation that would kill a human instantly. Bacteria reproduce in hours. A single bacterial cell can become a billion cells in less than a day under ideal conditions. Natural selection, operating on these timescales, can produce adaptations in years or decades that would take mammals millions of years to develop. 33 days is a long time in the life of a microbe. Long enough to bloom, reproduce, sporulate, wait, and bloom again. The orbital rhythm of K2-18b, punishing as it is, would be less a catastrophe for microbial life than a pulse, a heartbeat, a repeating cycle of abundance and scarcity that life could adapt to over millions of years, in the same way Earth life has adapted to the cycle of seasons. The ocean itself would buffer much of the thermal variation. Water has an enormous capacity to absorb heat without changing temperature dramatically. The deep ocean layers of K2-18b, if the ocean is deep, would be thermally stable across timescales of years or even decades. Only the uppermost surface would oscillate with the orbital rhythm. Life in the deeper layers might barely notice the difference between the close approach and the far point. For organisms living in the deep water column, conditions might be far more stable than the orbital mechanics would suggest. But depth brings its own challenges. The deeper you go in a high-pressure ocean beneath a massive hydrogen atmosphere, the more extreme the conditions become. Pressures that would crush a submarine is less than #0. 3# is greater than temperatures that climb as you descend toward whatever lies at the bottom. Darkness, because even the red light from K2-18 that penetrates deeply into the water column would be absorbed within hundreds of meters at most. Life in the deep ocean of K2-18b would be life in conditions that make the crushing darkness of the Mariana Trench look hospitable by comparison. And yet we know life can exist in exactly these kinds of environments on Earth. Hydrothermal vents on the ocean floor support entire ecosystems that have never seen sunlight. Communities of organisms powered by chemical energy from volcanic activity rather than photosynthesis. Tube worms meters long, blind shrimp, microbial mats so thick they look like living rock. These communities do not depend on the sun at all. They depend on the chemistry of hot water meeting cold water, of reduced chemical compounds meeting oxidized ones, of the energy released when electrons move from one molecule to another in the dark. If K2-18b has an ocean floor, and if that floor is geologically active, and if its interior generates heat the way Earth's interior generates heat, then the deep ocean of K2-18b could be just as alive as the deepest trenches on Earth, powered not by starlight, but by the planet itself. Now consider the atmosphere. Because the organisms that would produce detectable quantities of dimethyl sulfide would need to be in the upper ocean, close enough to the atmosphere for the molecule to escape into the air above. DMS is a volatile compound. It evaporates readily from the ocean's surface into the overlying atmosphere. On Earth, phytoplankton in the top few meters of the ocean produce it. It diffuses upward through the water column, breaks through the surface, and enters the atmosphere. The process is well understood and well characterized. On K2-18b, the same basic physics would apply. Whatever organisms produce DMS would need to be in the photic zone, the depth to which enough light penetrates to support energy harvesting chemistry, or at least near enough to the surface that the molecule can diffuse out before it is destroyed by pressure or temperature. The organisms themselves would be anaerobic. There is no free oxygen in K2-18b's atmosphere. Aerobic respiration, the process that powers every animal on Earth, including every human being listening to this, would be impossible. Life on K2-18b, if it exists, would be driven by anaerobic chemistry. The most likely candidates, by analogy with Earth's early life, are methanogens. Methanogens are archaea, ancient single-celled organisms that belong to one of the three domains of life on Earth, alongside bacteria and eukaryotes. They thrive in oxygen-free environments. They use hydrogen gas as an electron donor and carbon dioxide as an electron acceptor, combining the two to produce methane and water. They are among the most ancient organisms on Earth, possibly among the first forms of life to evolve after the origin of life itself. And K2-18b's atmosphere is rich in exactly the compounds they use as fuel. Hydrogen, carbon dioxide, both present in abundance, both detectable by JWST, and the methane they would produce as waste is also present in quantities that are themselves considered potentially significant. But methanogens alone do not fully explain the DMS. On Earth, DMS is not a methanogen product. It comes from a different metabolic pathway entirely, one involving sulfur chemistry rather than carbon chemistry. This raises an interesting possibility. Perhaps what we are seeing in K2-18b's atmosphere is not one type of organism, but the combined signature of an entire ecosystem. Methanogens driving the methane signal, sulfur metabolizing organisms driving the DMS. Multiple lineages of microbial life, each exploiting a different chemical gradient in the ocean, each producing their own atmospheric exhaust, all of it accumulating in a hydrogen sky that destroys these molecules more slowly than Earth's atmosphere does. An ecosystem, not an organism. The scale of biological activity required to explain the signal is genuinely staggering. Earth's oceans contain somewhere in the region of 25 trillion phytoplankton cells, producing roughly 100 million tons of DMS per year. That is the combined output of every ocean on this planet. K2-18b's DMS concentration is approximately 10,000 times higher than Earth's, is less than #0. 3# is greater than even, accounting for the slower destruction rate in a hydrogen atmosphere, which could reduce the required biological flux by a factor of 10 to 100. The numbers are still enormous. Either K2-18b's ocean is vastly more productive per unit volume than Earth's, with more life packed into each cubic meter of water, or the organisms have evolved DMS production pathways far more efficient than anything on Earth. Or DMS is not an accidental byproduct of some other metabolic process, as it is in Earth's phytoplankton, but a primary product, deliberately synthesized at high rates for reasons we cannot yet imagine. Any of these scenarios would describe biology utterly unlike anything we know. Not alien in the way science fiction imagines aliens, not tentacles and intelligence and deliberate communication, but alien in a deeper, more fundamental way. Biology shaped by completely different physical constraints, operating on completely different chemical substrates, under pressures and temperatures and radiation environments that have no analog on Earth. Life that evolved independently, from whatever chemistry gave rise to it, in an ocean that has never touched our world. Life that does not know we exist. Life that has no concept of being observed. Life that simply lives in the dark waters of a hydrogen sky world, exhaling the same chemical that coats every beach on Earth, without any idea that 124 light-years away, a species of clever, anxious, wandering primates is staring at a graph and asking whether they are alone. K2-18b, The Smell of Life, Chapter 9. The Science of Biosignatures. The word biosignature sounds precise, scientific, definitive. It sounds like the kind of term that, once applied, settles a question. But in practice, a biosignature is one of the most contested concepts in all of modern science, because every molecule that life produces, every gas that organisms exhale, every chemical signature that a living biosphere leaves in the atmosphere of its planet, geology and chemistry and physics can also produce, at least in theory, without a single cell ever having existed. The problem of biosignatures is not finding them. The problem is being certain that what you have found could not have gotten there any other way. Take oxygen. Free molecular oxygen in a planet's atmosphere is often cited as the ultimate biosignature. On Earth, it is a product of photosynthesis. Billions of years of plants and cyanobacteria splitting water molecules and releasing oxygen as waste. Before life existed, Earth's atmosphere had essentially no free oxygen. Life put it there. Surely then, detecting oxygen in the atmosphere of an exoplanet would be proof of life. Except that ultraviolet radiation can also split water molecules, releasing hydrogen into space and leaving oxygen behind. A water-rich planet close to an active star could build up significant atmospheric oxygen without a single photosynthetic organism ever evolving. The oxygen would be there. The life would not. Methane has the same problem. On Earth, atmospheric methane comes primarily from biological sources, livestock digestion, wetland decomposition, landfills, and natural gas systems. But methane also erupts from volcanoes. It seeps from the seafloor where geological processes create it in the absence of any biology. It forms in the atmospheres of gas giants through purely chemical means. Detecting methane tells you that carbon and hydrogen are present and that conditions favor their combination. It does not tell you that life is responsible. Phosphine, as we discussed in the previous chapter, fell into exactly this trap. And dimethyl sulfide, despite its remarkable specificity as a biological product on Earth, has now been found in cometary ice, confirming that abiotic production pathways exist even for this molecule. Every individual biosignature has an abiotic escape route. Every single one. And this is not a minor technical inconvenience. It is the central epistemological challenge of the entire field. The response from the astrobiology community has been to move away from the idea of a single silver bullet biosignature and toward what researchers now call biosignature ensembles. The concept is elegant and powerful. Instead of looking for one molecule and asking whether it could have gotten there without life, look for combinations of molecules that could only coexist in a living system. Individual molecules have abiotic escape routes. Combinations of specific molecules, maintained simultaneously against the tendency of chemistry to equilibrate towards simpler states, are much harder to explain without an ongoing biological source. The gold standard biosignature ensemble is oxygen combined with methane. These two molecules react with each other. In the presence of sunlight, oxygen and methane combine to form carbon dioxide and water. The reaction proceeds steadily, continuously, and in the absence of any replenishment, it would consume both molecules in a matter of thousands of years. A geologically short time. If an atmosphere contains both oxygen and methane simultaneously in significant quantities, something must be continuously producing both of them, replenishing the supply faster than chemistry consumes it. On Earth, life does exactly this. Photosynthesis produces oxygen. Methanogenic bacteria produce methane. The biosphere maintains both molecules in the atmosphere simultaneously against the thermodynamic pressure of the reactions that would destroy them. No purely geological or chemical process is known to produce both gases continuously at the rates required to maintain them together. This is why the oxygen-methane combination is considered the most diagnostic biosignature available. Not because either molecule alone is uniquely biological, but because their simultaneous presence implies an active, ongoing biological pump counteracting chemistry. K2-18b has methane. It does not, as far as current data shows, have detectable free oxygen. The absence of oxygen is not surprising given the hydrogen-dominated atmosphere, where oxygen would react with hydrogen and disappear almost immediately. But it means the gold standard ensemble is not available for this planet. The DMS signal, if real, represents a different kind of biosignature argument. Not the thermodynamic disequilibrium argument that underpins the oxygen-methane case, but a source strength argument. The concentration is so high that abiotic production cannot easily explain it. This is a weaker form of biosignature logic. It depends on our knowledge of all possible abiotic production rates being complete, which it is not. It depends on our atmospheric models being accurate enough to constrain the source strength required, which they may not be. And it depends on the detection itself being genuine, which, as we have seen, is contested. Sarah Seeger at MIT has been thinking about biosignature science longer than almost anyone in the field. In 2025, she published a preprint listing 15 candidate biosignature gases for exoplanet atmospheres. The list is remarkable, not for what it includes, but for what it implies. Among the 15 candidates are chlorofluorocarbons, synthetic chemicals that on Earth are produced only by industrial processes. Their detection in an exoplanet atmosphere would not just be a biosignature. It would be a technosignature, evidence not just of life, but of technological civilization. The list also includes molecular oxygen, nitrous oxide, methyl chloride, and several sulfur-containing compounds. Some of these overlap with what has been detected at K2-18b. Methyl chloride in particular, if detected alongside DMS, would provide significant independent biological evidence because the two molecules share no plausible common abiotic source pathway. The expansion of the biosignature target list reflects a maturing field. Early astrobiology was shaped too heavily by Earth as the template. The assumption was that life elsewhere would use the same metabolic pathways as life on Earth, produce the same waste gases, leave the same atmospheric fingerprints. That assumption is almost certainly wrong. Life on K2-18b, if it exists, evolved independently in a completely different environment. It may use metabolic strategies that have no analog on Earth. The molecules it produces may not even be on Seeger's list. The honest acknowledgement of this possibility is itself scientific progress. There is also the instrument problem, and it is a problem that cannot be wished away. The James Webb Space Telescope was conceived in the 1990s. At that time, the first exoplanet orbiting a sun-like star had not yet been confirmed. Sub-Neptunes were unknown. The idea of characterizing exoplanet atmospheres for biosignatures was not part of the telescope's original design brief. JWST was built to observe galaxy formation, stellar nurseries, and the early universe. Its ability to analyze exoplanet atmospheres is, in the language of engineers, A bonus feature. A remarkable, unexpected, science-transforming bonus feature. But a bonus nonetheless. This means that JWST is, for this particular application, operating at or near the limits of what its design allows. The signal-to-noise ratio for molecules at K2-18b is close to the instrument's noise floor. Small calibration errors, small modeling assumptions, small decisions about how to process the raw data can change the apparent strength of a molecular detection significantly. This is not a flaw in the telescope. It is simply the reality of asking an instrument to do something it was not specifically designed to do. The ambiguity in the K2-18b data is not a failure of science. It is the telescope being pushed to its frontier and finding the frontier harder than it looks. The instruments being built now are a different story. The extremely large telescope, a 39-meter behemoth being constructed on a mountaintop in the Atacama Desert of Chile, will have 6 times the light-collecting area of JWST. It will be able to resolve individual molecular features that JWST blurs together. It will be capable of detecting the oxygen-methane combination in the atmospheres of rocky planets around nearby red dwarf stars, a detection completely beyond JWST's capabilities. First light is expected around 2030. And beyond the extremely large telescope, NASA's Habitable Worlds Observatory, planned for launch in the 2040s, is being designed from scratch for one specific purpose: directly imaging Earth-like planets around Sun-like stars and analyzing their atmospheres for biosignatures, not transiting sub-Neptunes, true Earth analogues. Planets orbiting in the habitable zones of stars like our own Sun, imaged directly, their light separated from the overwhelming glare of their parent stars, their atmospheric spectra measured in detail, sufficient to search for the full range of biosignature ensembles. K2-18b will almost certainly be resolved, one way or another, long before the Habitable Worlds Observatory launches. The question of whether it harbors life is a JWST question, answerable with instruments that already exist, aimed at a planet already identified. The question of whether Earth-like life exists on Earth-like planets around Sun-like stars is a question for the next generation of instruments and the generation of scientists who are, right now, perhaps still in school, who will spend their careers building and using those instruments to find an answer. The science of biosignatures is young. 20 years ago, it barely existed as a formal discipline. Today, it has journals, conferences, dedicated research groups, and an increasingly sophisticated theoretical framework. It is driven by a question so fundamental that it needs no justification. It is driven by the oldest question there is: are we alone? And K2-18b, right now, in 2026, is the closest we have ever come to a data-based answer. K2-18b, The Smell of Life. Chapter 10, The Great Debate. There is a building on the west side of Cambridge, England, where 2 research groups work within walking distance of each other. Both groups are well-funded. Both are respected. Both are staffed by serious, careful, talented scientists who have spent years studying the same planet. One group believes K2-18b may be a Haitian world with a hydrogen ocean, potentially harboring microbial life. The other believes it is almost certainly a magma world with a chemistry that mimics biology without containing any. They are not enemies. They are colleagues. They almost certainly pass each other in the corridor, share seminar rooms, perhaps even have lunch together occasionally. And they think each other is wrong about the most important scientific question of the century. This is, in fact, exactly how science is supposed to work. Not as a unified march toward consensus, but as a contest of ideas in which evidence is the only judge and the best argument, tested against the most rigorous scrutiny available, eventually wins. The Cambridge debate over K2-18b is not a dysfunction of the scientific process. It is the scientific process, running at full intensity, applied to a question that matters enormously. But it is also, unavoidably, a deeply human story. Because the scientists involved are human beings with reputations, with careers, with the very natural desire to be the person who got it right. Niku Madhusudan came to astronomy from theoretical physics. He is Indian-born, Cambridge-educated, and has spent the better part of 2 decades building some of the most sophisticated atmospheric retrieval models in the field. His 2021 Heischen paper was a theoretical framework, an argument that a class of planets previously dismissed as uninhabitable might be among the most promising targets for biosignature searches. It was a bold claim, and it was met with the skepticism that bold claims always attract. When the JWST data began to come in and match his predictions, he described the experience as surreal, as if something he had imagined in mathematics had suddenly materialized in an observation. The moment in April of 2025 when the MIRI data confirmed the near-infrared signal was, by his own account, transformative. A shock to the system. He chose his words carefully in the weeks that followed. He consistently said potential biosignature, possible indicators. He did not say life detected. He understood, with the clarity of someone who has spent a career in science, what the difference between those phrases means and what the consequences of blurring them would be. But the media did not make that distinction. When Cambridge released the April 2025 results, the headlines were immediate and almost uniformly breathless. Life found on alien planet. Scientists detect signs of life 100 light-years away. The ocean world that smells of life. Researchers who had not been involved in the study and had not yet seen the full data began receiving calls from journalists asking for their reaction to the discovery of extraterrestrial life. Not the potential indication of biosignatures at 3 sigma statistical confidence. The discovery of life. The response from the community was swift and, in some corners, furious. Several senior scientists publicly accused the Cambridge team of jumping the gun, of releasing results that were not ready for the level of public attention they were about to receive, of creating a media environment that would be almost impossible to walk back if the signal turned out to be a noise artifact or an exotic chemistry explanation. One scientist, speaking off the record, compared it directly to the phosphine affair and said the field could not afford another cycle of hype and retraction. Madhusudan pushed back on this characterization in interviews. He pointed out that his team had been scrupulously careful in their language, that the paper itself used qualified, precise, scientifically appropriate phrasing throughout, that the media's translation of potential biosignature into life found was not something he had control over or had encouraged, and that the alternative, saying nothing while sitting on a result of this potential magnitude, was not obviously the right choice either. He was making a legitimate point. The tension between scientific caution and public communication is not unique to this case. It runs through every major scientific announcement in history. The researchers who work for years on a result have an obligation to communicate it accurately is less than #0. 3# is greater than. They do not have the ability to control what happens to that communication once it enters the media ecosystem. The amplification, the simplification, the emotional loading that turns a qualified statistical claim into a declaration of discovery, that is, a structural problem of how science journalism works, not a failure of any individual scientist. Meanwhile, in offices not far from Madhusudan's, Oliver Shortall was doing his own work. Shortall is a geochemist by training, someone who thinks about planets from the inside out. Where Madhusudan's models start with the atmosphere and work inward, Shortall's models start with the rocky interior and work outward. His approach to K2-18b was not to ask what atmospheric composition life would produce, but to ask what atmospheric composition a planet of this mass and composition would produce through purely geological processes. The answer, his models showed, was uncomfortably similar to what JWST observed. A magma ocean at the base of the atmosphere would dissolve nitrogen. It would release methane and carbon dioxide through volcanic outgassing. It would suppress ammonia through chemical reactions with the molten rock. The atmospheric fingerprint of a lifeless magma world and the atmospheric fingerprint of a biologically active Haitian ocean are, within the resolution of current observations, essentially indistinguishable. Shortall has been careful not to claim that K2-18b is definitely a magma world. He claims only that the data is consistent with a magma world, just as it is consistent with a Haitian world. The point is not that the biological interpretation is wrong. The point is that it is not the only interpretation. And in science, when two interpretations both fit the available data, the simpler one, the one that requires fewer extraordinary assumptions, is the one you favor until evidence distinguishes between them. A magma world producing methane and CO2 through volcanic chemistry requires no new physics, no novel biochemistry, no extraordinary coincidence of conditions. It requires only that K2-18b behave like the class of planet its mass and density suggest it might be. A Haitian world with a biological ocean requires liquid water, a hydrogen atmosphere at just the right temperature, the independent origin of life, the evolution of organisms capable of surviving extreme pressure and radiation, and the coincidental production of DMS at exactly the concentrations JWST is detecting. By the principle known as Occam's razor, the magma world is the simpler explanation. Simplicity is not proof, but it is a tiebreaker. And yet there is one response to this argument that carries real weight. The Haitian hypothesis did not emerge after the observation. It emerged 4 years before it. Madhusudan's 2021 paper predicted that if life existed on this kind of world, DMS would be detectable at these concentrations. The magma ocean models, whatever their merits, were developed largely in response to the detection as alternative explanations for data that already existed. Predictive success carries epistemological weight that post hoc explanation does not. A theory that tells you what you will find before you look is, all else being equal, stronger than a theory that tells you why what you found makes sense after the fact. Both camps have published rigorous work, but the asymmetry of prediction versus explanation is real, and it tilts the scales slightly toward taking the biological interpretation seriously. The most revealing thing Madhusudan said about the entire process was not about the data. It was about the months of work that preceded the announcement. He said his team spent that time actively trying to get rid of the signal, not trying to confirm it, not building the case for it, trying to destroy it, testing every calibration assumption, modeling every alternative molecule, looking for every possible explanation that did not involve life, and finding, after months of this, that the signal persisted. That is what good science looks like from the inside, not the triumphant announcement, the long, unglamorous, methodical attempt to prove yourself wrong, and the strange, uncomfortable feeling when you cannot. The debate over K2-18b is not resolved. It will not be resolved by argument alone. It will be resolved by data, by more transits observed through more instruments at more wavelengths, by better atmospheric models constrained by better measurements, by the slow accumulation of statistical weight that either solidifies the signal or erases it. Both camps know this. Both are waiting. Both have submitted proposals for additional telescope time. Both will analyze whatever comes next with the same rigor they have brought to what has come before. The answer exists. It is encoded in the light that left K2 negative 18,124 years ago and is arriving at our telescopes right now. We just have to be patient enough and rigorous enough to read it correctly. K2-18b, The Smell of Life, Chapter 11. The world that might be alive. Close your eyes for a moment. Or let them rest, half open, the way they do when you are drifting between thought and sleep. And try to build a world. You are not on Earth. There are no reference points. No familiar horizon. No blue sky overhead. No yellow circle of the sun moving through its daily arc. The sun you knew is gone. 124 light years gone. What hangs above you instead is something older, dimmer, redder. A star the color of cooling iron, large in the sky because you are so close to it, but casting a light that is thick and amber rather than white and sharp. A permanent twilight, even at midday. Reddish shadows that fall in directions that never change, because this star does not move. It has never moved. Not once, in all the billions of years this world has existed, has the star shifted from its position on the horizon of the dayside. You are on the terminator, the ring of perpetual dusk that circles the planet where day becomes night. It is the only place on this world where temperatures are moderate enough to sustain the chemistry of life. Behind you, the dayside blazes in permanent amber noon, the atmosphere heated and expanding, hydrogen wind screaming from hot to cold at hundreds of miles per hour. Before you, the night side is black and frozen, temperatures plunging to 60 degrees below zero and lower, a landscape of eternal dark that has never seen direct starlight and never will. Where you stand, the wind is constant, a roar of hydrogen rushing from the hot world behind you toward the frozen world ahead. It carries with it a smell, not subtle, not the gentle marine scent of a summer beach at low tide. Something overwhelming, saturating, impossible to ignore. The combined chemical exhalation of a planet-wide ocean, 10,000 times more potent than anything Earth's seas produce. If you could breathe this air, which you cannot, because there is no oxygen in it, you would be engulfed by the smell of life. Life you cannot see, life you cannot touch, life that exists somewhere beneath you in the crushing dark of an ocean that has no shore. Look down. If the Hessian hypothesis is correct, beneath the hydrogen atmosphere, there is water. Not the clear, sunlit water of a tropical sea. Dense, pressurized, dark. Water that has been under the weight of a massive hydrogen sky for billions of years. Water at temperatures and pressures that have no equivalent anywhere in Earth's oceans. Surface pressure, perhaps 100 times greater than sea level on Earth. Temperatures at the upper layers perhaps 50 to 90 degrees Celsius. Hot enough to burn skin instantly, but cool enough, under that pressure, to remain liquid. The water stretches from here to the other side of the planet with no interruption. No continents. No islands, no shallow reef, just water all the way down to whatever lies beneath. The upper layers of this ocean are where the Dimethyl Sulfide signal comes from, if it comes from life at all. Imagine the surface from below, the hydrogen atmosphere above, thick and pressing. The faint reddish light from K-18 filtering down through the first few meters of water, dimming rapidly as it descends, until a few hundred meters down there is no light at all. In that thin, warm, lit zone near the surface, if life exists here, it blooms. Microbial mats perhaps, or something for which we have no name, single-celled organisms metabolizing sulfur and carbon and hydrogen in combinations that Earth chemistry has never produced. Their metabolic waste drifting upward through the water column, breaking through the surface tension, dissolving into the hydrogen atmosphere above, accumulating, building up over time. Because in this atmosphere, the molecules last longer than they would in oxygen-rich air. They persist. They travel. They spread around the entire planet on the hydrogen wind until the atmosphere is saturated with their presence, soaked in the chemical evidence of something alive far below. Go deeper. Below the photic zone, below the last trace of starlight, the ocean becomes something else entirely. Cold and dark and under pressure that would compress a steel cylinder to the size of a fist. If anything lives here, it lives without light, without the energy that drives almost all life on Earth's surface. But the planet generates heat from within. The massive rocky and icy interior, compressed and churning under its own gravity, releases thermal energy upward through the water column. Somewhere in the deep, perhaps, there are hydrothermal vents. Cracks in whatever lies at the bottom of this ocean, where superhot fluid, rich in reduced chemical compounds, erupts into the cold, dark water above. Around those vents, if they exist, there could be ecosystems that have never needed the star at all, that have been living in the deep dark since before the planet was old enough to be called old, that have been metabolizing and evolving and diversifying for 2 billion years in a world that makes the deepest trench on Earth look like a sunlit swimming pool. We would not see these organisms in our atmospheric signal. They would leave no trace in the spectra JWST collects. They would simply exist in the cold and the pressure and the dark, indifferent to our instruments. Now consider the alternative, the magma world. The atmosphere is the same. The hydrogen sky, the reddish star, the terminator wind is less than #0. 3# is greater than. From above, from the perspective of a telescope 124 light-years away, it looks identical. But below the atmosphere, there is no ocean. There is rock, molten rock, glowing at temperatures of thousands of degrees, churning with convection currents that bring material up from the deep interior in slow, massive rolls that take centuries or millennia to complete a single cycle. The surface, if you can call it that, is a sea of orange and red, lit from below by its own heat, casting a dim glow upward into the base of the hydrogen atmosphere. Where magma meets atmosphere, violent chemical reactions occur continuously. Volcanic gases erupt upward. Nitrogen dissolves downward into the melt. Methane forms at the boundary where high-temperature carbon chemistry produces organic compounds without any biology required. And somewhere in this violent, sterile, beautiful hell, dimethyl sulfide forms too, at low yields, slowly, but continuously, over billions of years, building up in the long-lived hydrogen atmosphere until the concentration reaches a level that a telescope 124 light-years away picks up as a potential biosignature. No life, no ocean, no organisms in the dark water, just chemistry, ancient and indifferent, producing the same smell as a billion phytoplankton blooms for completely different reasons. These two worlds are the same world, same distance from us, same size, same atmospheric composition as far as our instruments can determine, separated not by any measurement we can currently make, but by a physical reality we have not yet been able to access from this distance. One is a living world, one is a dead one, and from where we sit, we cannot tell them apart. There is something philosophically striking about this situation that goes beyond the immediate question of whether K2-18b harbors life. We have built an instrument of extraordinary sophistication. We have pointed it at a planet 124 light-years away. We have detected molecules in its atmosphere at concentrations of parts per billion from a distance so vast that the light we are analyzing has been traveling since before the ancient Greeks built their first temples. We have done all of this, and we still cannot answer the most basic question: is anything alive there? The universe is not making this easy for us. It is not arranging things so that the answer is obvious. It is presenting us with a signal that is genuinely ambiguous, a world that presents two completely different faces depending on which set of models you trust. A debate that cannot be resolved by cleverness alone, but only by more data, more time, more observations. Perhaps that is appropriate. The question of whether life exists beyond Earth is not the kind of question that should have an easy answer. It should require everything we have, all the ingenuity and patience and rigor we can bring to it. It should make us work, and it should make us wonder, in the meantime, at the sheer audacity of asking it at all. 124 light-years away, something is there. A world, real and physical, with an atmosphere and an interior and a surface of some kind, spinning slowly, locked to its red star, breathing out chemistry into the hydrogen wind, waiting, without knowing it is waiting, for the data to come in. K218b, The Smell of Life. Chapter 12, The Philosophy of Finding Life. Imagine, for a moment, that the signal holds, that the additional observations come in over the next 12 to 18 months, and the statistical confidence climbs. 4 sigma. Then 5. That the magma ocean models are ruled out by new data, showing atmospheric features inconsistent with a lifeless chemistry. That methyl chloride is detected alongside DMS, closing the abiotic escape routes. That a press conference is scheduled, and the world stops to listen. What happens next? Not to the science, to us. This is not a question scientists are trained to answer. It is a question for philosophers, theologians, psychologists, and anyone who has ever looked up at the night sky and felt the full weight of what is out there. And it is a question that deserves serious thought before the answer arrives, not after. Because if the confirmation comes, it will come fast. Not with the slow build-up of a war or the gradual transformation of a cultural movement. With a press conference, a graph, a statistical threshold crossed. And then, within hours, every person on Earth will know. Begin with the Fermi paradox. In 1950, the physicist Enrico Fermi was having lunch with colleagues and posed a question that has haunted science ever since. If the universe is so vast, if there are so many stars, if the conditions for life are not uncommon, where is everyone? Why have we not heard from any other civilization? Why is the galaxy not teeming with signals and probes and evidence of other minds? The Fermi paradox has no satisfying answer. Dozens of proposed solutions exist, and none of them fully account for the silence. Either life is extraordinarily rare, or intelligence is extraordinarily rare, or civilizations destroy themselves before they can communicate, or something else, something we have not yet imagined, explains why the universe appears so empty of other voices. A confirmed detection of microbial life on K218b would transform this calculation instantly. If life arose independently on K218b, one of the first habitable zone planets we examined closely, that tells us something staggering about the universe. It tells us that life is not a singular miracle, a one-time accident on one lucky planet around one ordinary star. It tells us that life is something the universe does, a process, not an exception. Something that emerges, perhaps inevitably, wherever the conditions permit. And if life is common, then intelligence, however rare it might be, is not impossible across the vast numbers of planets in the galaxy, which means the Fermi paradox sharpens dramatically. If life is everywhere, where are the civilizations? The great filter, the hypothetical barrier that prevents life from becoming spacefaring civilization, either lies behind us, already past, or it lies ahead. And if it lies ahead, that is the most disturbing implication of all. The history of human cosmology is a history of successive demotions. Each major discovery has moved us further from the center of things. The Earth orbits the Sun, not the reverse. The Sun is one of 400 billion stars in the Milky Way. The Milky Way is one of perhaps 2 trillion galaxies in the observable universe. Each demotion was philosophically traumatic in its time. Copernicus's heliocentrism was heresy before it was science. The expanding universe was greeted with resistance even by Einstein, who added a cosmological constant to his equations, specifically to prevent it from implying a beginning. The confirmation of extraterrestrial life would be the next great demotion. The last remaining claim to cosmic uniqueness, that Earth is the only world where chemistry became biology, would be gone. We would no longer be able to say that life is what makes our planet special. Life, it turns out, is what the universe makes. Earth is just one of the places where it happened. Some people will find this devastating. The sense that humanity, that life itself, is special, unrepeatable, uniquely significant in a vast, indifferent cosmos, is deeply embedded in most human cultures and most human religions. A confirmation that we are not unique, that microbes in a hydrogen ocean 124 light-years away are as much a manifestation of life as we are, would challenge frameworks that billions of people use to understand their existence. And yet the major religious traditions have been thinking about this question seriously for decades. The Vatican's Pontifical Academy of Sciences has addressed the question of extraterrestrial life multiple times, with official positions ranging from open curiosity to the view that the existence of life elsewhere would not challenge fundamental theological claims. The argument is roughly this: if God created the universe, and if life is something the universe produces under the right conditions, then the existence of life beyond Earth is simply an expression of the same creative principle, not a threat to theology, an expansion of it. Buddhist and Hindu frameworks, which do not center human beings as uniquely spiritually significant in the same way Western traditions sometimes do, have arguably even less to reconcile with the confirmation of extraterrestrial life. Indigenous cosmological frameworks from cultures around the world have, in many cases, always understood the cosmos as populated with living things in ways that Western science is only now beginning to validate. The psychological research on how people would actually respond to a confirmed detection of extraterrestrial life suggests something interesting. Multiple surveys conducted in recent years, including studies by researchers at the University of Arizona and the SETI Institute, have found that most people, when asked directly, say they expect to feel positive about such a discovery. Curious, excited, perhaps awed. The expected devastation, the civilizational crisis that some commentators predict, does not match what people say they would actually experience. This could reflect genuine resilience, or it could reflect the difficulty of truly imagining what such a confirmation would feel like from the inside. We have no precedent. We are guessing about our own reactions to something that has never happened before. What seems clear is that the confirmation would not arrive with the drama of a science fiction film. No alien ship in the sky. No signal from a distant civilization. No contact, no communication, no presence we could point to in the night and say there, look. Just a graph with a curve that crosses a threshold, and a press release, and a scientist at a podium saying the words carefully, one at a time, because the words matter, and he knows it. And then the world absorbs it, in the way the world absorbs everything, through argument and reaction and gradual, uneven integration into the stories we tell about who we are and where we come from. Michael Wong, an astrobiologist at Carnegie Science, looked at the state of the field in April of 2025 and said something simple and true. What a lucky time to be alive. He was right. We are the first generation of human beings to have the instruments, the knowledge, and the planetary targets to ask this question with real data. We are alive in the decade, possibly the year, when the answer to the oldest question in human history may be found. Not through revelation, not through philosophy, not through the long, slow work of theology, but through a spectrograph pointed at a star 124 light-years away, reading the chemistry of an alien sky, one photon at a time. Whatever the answer is, we are the first to be close enough to ask. K2-18b. The Smell of Life. Chapter 13. What happens next? Science does not end with a detection. It begins with one. Everything we have covered in this documentary, the signal, the debate, the alternative models, the false positives, the philosophy, all of it is prologue. The question of whether K2-18b harbors life is not going to be answered by reviewing what we already know. It is going to be answered by observations that have not yet been made, by analysis that has not yet been completed, by data that may be sitting in a telescope queue right now, waiting its turn. So let us talk about what those observations look like, what they would tell us, and how long we might have to wait for the answer. The James Webb Space Telescope has observed K2-18b twice in transit. Once in 2023 using the near-infrared instruments, and once in 2025 using MIRI. Each transit window lasts roughly 8 hours, the duration of the planet's crossing of its star's face as seen from Earth. Each observation adds photons to the dataset, increasing the signal-to-noise ratio and pushing the statistical confidence either upward if the signal is real or downward if it is noise. The current confidence level of 3 sigma was built from 2 observations. 2 to 3 additional transit observations, analyzed together with the existing data, would either push the confidence above 5 sigma and into discovery territory, or reveal that the signal weakens with more data, suggesting it was a statistical fluctuation. The planet transits every 33 days. The geometry that allows a transit to be observed from Earth does not occur every orbit, but JWST's orbital position gives it favorable viewing windows several times per year. The limiting factor is not the planet's availability. It is telescope time. JWST is the most oversubscribed scientific instrument in human history. Thousands of research groups from dozens of countries submit proposals for observing time each year. A review panel assesses each proposal on its scientific merit and allocates time accordingly. The Cambridge team has submitted proposals for additional K2-18b observations. Whether those proposals are approved and when determines the timeline for reaching 5 sigma. If additional time is granted and the observations are completed without technical issues, the 5 sigma threshold could potentially be reached within 12 to 18 months of the April 2025 announcement, potentially by mid-2026 or late 2026. The data, in other words, may already be flowing. The analysis may already be underway in offices in Cambridge and in competing groups around the world, each applying their own methods to the same raw photons. But 5 sigma is not the only thing the additional observations need to accomplish. Statistical confidence is necessary, but not sufficient. To make a credible case for a biosignature, the Cambridge team also needs to narrow the molecular identification. Dimethyl sulfide and dimethyl disulfide, 2 related sulfur-containing organic molecules, have overlapping spectral features at the wavelengths JWST has examined. Distinguishing between them requires longer wavelength data, in the range beyond 12 microns, where their absorption features diverge. MIRI can access some of this range, but pushing further into the mid-infrared requires observations that have not yet been conducted. Knowing which molecule is present matters for the biological interpretation. Both DMS and DMDS are consistent with biological sources, but their production mechanisms differ, and identifying which one is dominant would help constrain the chemical models on both sides of the debate. The molecule that would provide the most powerful additional evidence is methyl chloride. On Earth, methyl chloride is produced primarily by vegetation and marine organisms. It has no known abiotic production pathway that would generate it at atmospheric concentrations in the environment of a sub-Neptune. Its spectral features lie in a range accessible to JWST, and a detection of methyl chloride at K2-18b alongside the DMS signal would represent a genuinely independent line of biological evidence. 2 molecules with no common abiotic source, both present simultaneously, would dramatically reduce the parameter space available to geological explanations. Conversely, the detection of ethane would complicate the biological picture. Ethane appears alongside DMS in Earth's atmosphere, but is absent from the current K2-18b data. If future observations confirm that ethane is genuinely absent, that absence itself becomes an informative constraint, telling us something about the chemical environment that may favor or disfavor particular interpretations. Beyond JWST, the scientific infrastructure being built right now will transform what is possible within a decade. The extremely large telescope is a 39-meter diameter optical and infrared telescope under construction at the Cerro Armazón site in the Atacama Desert of Chile. Its primary mirror, composed of 798 individual hexagonal segments, will have a light-collecting area roughly 6 times greater than JWST's. First light is expected around 2030. For exoplanet atmosphere characterization, the ELT represents a qualitative leap. Its high-resolution spectrographs will be able to resolve individual molecular absorption lines that JWST blurs into broad features, dramatically reducing ambiguity in molecular identification. For K2-18b specifically, the ELT may offer limited improvement because its design is optimized for smaller, rockier planets around nearby stars rather than sub-Neptunes at K2-18b's distance. But for the broader search for biosignatures in nearby red dwarf systems, the ELT will be transformative. Planets like TRAPPIST, 1e, and Proxima Centauri b, rocky worlds, potentially in the habitable zones of red dwarfs within 40 light-years of Earth, will be accessible to the ELT's characterization capabilities in ways they are not to JWST. Further out, the Habitable Worlds Observatory represents the most ambitious planetary science mission ever proposed. Designed by NASA as the successor to JWST for exoplanet science, it would be a large space telescope optimized for the direct imaging of Earth-like planets around Sun-like stars, not transiting sub-Neptunes. True Earth analogues in the habitable zones of stars like our own Sun. Their light directly imaged, separated from the star's glare by a starshade or coronagraph. Their atmospheric spectra measured in enough detail to search for the oxygen-methane ensemble and a wide range of other biosignature combinations. Launch is planned for sometime in the 2040s. By the time the Habitable Worlds Observatory launches, K2-18b will either have been confirmed as a living world, ruled out as a magma world, or its signal will have been reassigned to some exotic chemistry we have not yet imagined. The planet that is driving the most intense astrobiological debate of the 2020s will have been resolved, one way or another, using instruments that already exist. The Habitable Worlds Observatory will inherit a field that has already answered the K2-18b question and is ready to ask the next one. And there is something important in that timeline. The answer to whether K2-18b is alive is not a problem for future generations. It is a problem for this generation. For the scientists currently working in Cambridge and Oxford and Chicago and Zurich and 100 other institutions. For the graduate students who submitted their applications to work on exoplanet atmospheres because of the 2023 announcement and are now writing their first papers. For the review committees deciding how to allocate telescope time. For you, if you follow this story as it develops, which you might, because the next significant data release when it comes is not going to be buried in a technical journal that takes a year to filter into popular awareness. It is going to be front-page news within hours of the preprint appearing online. The infrastructure for communicating science to the public has never been faster. The infrastructure for receiving it has never been more prepared. People know about K2-18b now. They are waiting. The planet transits again soon, and somewhere in the data that comes back, the answer is encoded is less than #0. 3# is greater than waiting to be read. K2-18b The Smell of Life. Chapter 14. The answer at the edge of knowing. There is a particular kind of silence that falls at the end of a long question. Not the silence of emptiness, but the silence of waiting. The silence of a held breath, of something about to resolve. That is where we are right now, in the spring of 2026, in the story of K2-18b, at the edge of knowing, close enough to the answer to feel its gravity, but not yet across the threshold that would turn a signal into a discovery, a possibility into a fact. Tonight, we are going to sit with that threshold and think about what is on both sides of it. Scenario 1. The signal disappears. The next transit observations come in. The data is processed. The statistical analysis is run, and the confidence level drops. The curve that was pointing upward flattens. The DMS feature that seemed so compelling in two instruments' data turns out to be a noise artifact that accumulated over limited observations and dissolves when more photons are added to the dataset. Or it turns out to be dimethyl disulfide after all, a molecule that has plausible abiotic production pathways at K2-18b's temperatures and pressures. Or the magma ocean models, refined with new data about the planet's thermal emission, turn out to match the spectrum so precisely that the biological interpretation becomes redundant. K2-18b is a magma world. The smell of the sea was chemistry, not life. The ocean was never there. What does this mean? It means we were not fooled by wishful thinking. It means the scientific process worked. It means that demanding 5 sigma before declaring a discovery was the right call, because the signal that looked so compelling at 3 sigma turned out to be insufficient. It means that the methods developed during the controversy, Jake Taylor's unbiased retrieval analysis, Oliver Shortle's magma atmosphere chemistry models, Sarah Seeger's expanded biosignature catalog, all of these are permanent contributions to the field, regardless of the outcome at this particular planet. And it means the search continues. Not with disappointment, not with the deflation of a dream collapsing, but with the accumulated wisdom of a near miss applied to the next target. And there are more targets, dozens of sub-Neptunes in habitable zones identified by JWST and its predecessor missions. Rocky planets around nearby red dwarfs that the extremely large telescope will characterize in the 2030s. The entire catalogue of potentially habitable worlds that will be the Habitable Worlds Observatory's first priority in the 2040s. K2-18b was the first close look. It will not be the last. If life is out there, and there is no scientific reason to believe it is not, we will find it eventually. The tools are getting better. The methods are getting sharper. The catalogue of targets is growing. A false result at K2-18b is not the end of the story. It is the end of a chapter, and the next chapter begins immediately. Scenario 2. The signal holds. The transit observations come in. The confidence climbs. 4 sigma. The team waits. Another observation window. Another careful analysis. The curve crosses 5. Independent teams at other institutions run their own analyses on the same raw data using different methods and return the same answer. Methyl chloride is detected alongside DMS. The magma ocean models are ruled out by thermal emission data inconsistent with a molten surface. The abiotic production arguments run out of parameter space. There is a press conference. The room is very quiet, and Niku Madhusudhan, standing at a podium, says what he has been careful not to say for 3 years. Not potential indicators. Not possible biosignature. Life. Microbial. Alien. 124 light-years away. In an ocean we will never visit. Under a sky of hydrogen, orbiting a red star that most people on Earth have never heard of. Producing the same molecule that coats every beach on Earth. exhaling the smell of the sea into a world nothing like the sea. Alive. The world absorbs this fact. Not instantly, not uniformly. Some people feel it immediately, a physical shift in their understanding of their place in things. Some people need days or weeks before the scale of it settles. Some find it confirms what they always believed. Some find it challenges beliefs they did not know they held. Religions engage. Philosophers write. Children ask their parents questions that the parents cannot answer. And then something else happens. Something that may be the most important consequence of all. Every star in the sky becomes a question. Not a poetic question, a scientific one, with real targets and real instruments and real funding attached to it. If life arose independently on K2-18b, one of the first habitable zone planets we looked at carefully, then the galaxy is not a vast, sterile emptiness punctuated by one miraculous exception. The galaxy is a place where life happens. Routinely, perhaps inevitably, in hydrogen oceans and rocky crusts and chemical soups of types we have not yet imagined. The question shifts from whether life exists beyond Earth to where it does not. And the Fermi paradox sharpens into something genuinely unsettling. Because, if life is everywhere, and intelligence is possible, then the silence of the cosmos is not a comfort. It is a warning. Something happens to civilizations that prevents them from lasting long enough to make themselves known. And we, a young, anxious civilization that has had nuclear weapons for 80 years and a warming atmosphere for 30, need to think carefully about what that something might be. But set that thought aside for now. It is real, and it is worth sitting with another time. Tonight, in this quiet hour before sleep, let a different thought settle in. 124 light-years from here, there is a world. It is real. It is out there right now, orbiting its red star on its 33-day rhythm, its hydrogen atmosphere churning in the eternal wind from day to night, its surface, whatever surface it has, pressing up against the weight of the sky above it. Whether it is alive or not, we do not yet fully know, but we are asking. With the most powerful instruments our civilization has ever built, pointed at the sky, reading light that left that world over a century ago, we are asking the question that every human being who has ever lived has carried somewhere in them. Are we alone? The ancient astronomers who named the constellations could not have asked it with data. The philosophers who first proposed that other worlds might exist could not have measured an answer. The scientists who built the first telescopes and turned them on the night sky were centuries away from the instruments needed to even frame the question properly. We are the first generation in the entire history of our species to be close enough to an answer to feel it. Not to have it, not yet, but to feel it approaching, to see the curve climbing on a graph. To know that the data is out there, encoded in photons already collected or soon to be, waiting in a telescope's archive or a scientist's queue, patient in the way that light is patient, carrying its message across the darkness at the only speed the universe allows. Somewhere out there, something may be alive. Something that has never known us, that has no concept of our existence, that simply lives in its hydrogen ocean and exhales its chemistry into the alien sky above, day after 33-day year after billion year, without knowing that one day a species of curious, frightened, wondering creatures on a small blue planet in a distant part of the galaxy would point their finest instrument at the light of their star and read the signature of their breathing. We are asking, and the universe, in its way, may finally be answering. The stars are still out there, the same stars that have been watching every human generation from the beginning. They do not care about the question. They never have. But somewhere among them, 124 light-years in the direction of Leo, A dim red star is burning, and around it, a world is turning, locked to its star, breathing out, smelling of the sea,